And now is it working?
Yes, that's great.
And if I move, it moves.
Yeah.
Okay, good. Thank you.
Okay, we can start.
Okay, so it's my great pleasure to introduce the second speaker of the session. It's going to be Jessica Guerand, and she is going to talk about quantitative De Giorgi method for kinetic Fokker-Planck equation. Please go ahead.
Thanks a lot for the invitation. So yes, I'm going to talk about work we did with Clément. So now I'm in Montpellier, but in the previous years I was doing a postdoc in Cambridge. And we worked on the kinetic Fokker-Planck equation, more precisely on getting regularity for this equation. So quantitative regularity. Let me first start with a summary of the results and the talk. So yeah, we studied the quantitative regularity property of the kinetic Fokker-Planck equation, which is written here. So it's an equation with a transport term and a drift diffusion term, which can allow the source term as well. So it's an hyperelliptic equation in divergence form. And so the property we are interested in are the Hölder continuity and some Harnack inequalities. And the main assumption we make on this equation is that the coefficient is supposed to be rough. It means that they are only measurable. And they also satisfy some bounds that I wrote just here. So I'm going to explain the fact that we use rough coefficients will be useful to deal with the Landau-Coulomb equation. I will explain why. And this theory of dealing with linear equation with rough coefficients, it has been introduced by the techniques of De Giorgi, Nash-Moser. And I'm going first to explain how why these techniques have been introduced. And I'm also putting in the summary some open questions. So here we have the divergence form, but in the non-divergence form case, we don't know how to do, and it's an open question, and we're wondering if we can use the tools that we use here to deal with this case as well. And so with Clément, we've focused mainly on the De Giorgi method. So let me give a short historic of why dealing with these rough coefficients here. So it has been introduced in the first place to be able to solve the 19th Hilbert problem. So first, De Giorgi proved that's the solution of this linear equation with rough coefficient Hölder continuous. And it allows him to solve the 19th Hilbert problem, which states that the local minimizer of an energy functional of this type are analytic. So where we know that the function f here is strictly convex. And we know that those local minimizers satisfies an Euler-Lagrange equation, which takes this form and it's nonlinear. When we derive this Euler-Lagrange equation with respect of one variable, then we get this new equation, which is still nonlinear. But the idea of De Giorgi is to see it as a linear one, where you put you see this coefficient as general matrix that you call A of x, and then the equation becomes linear. And if you prove the Hölder continuity for this equation, then you get the Hölder continuity for the derivative of the local minimizer. And at this time, we already had the Schauder estimates. So with a bootstrap argument, it was remaining available. You just conclude that you can go from C1 alpha to C infinity using the Schauder estimates. So it was exactly the missing step to prove the 19th Hilbert problem at this time. At the same time, Nash solved independently with other techniques both the elliptic and the parabolic equation, so with rough coefficients. So he uses other techniques. So instead of using the perimetric arguments that De Giorgi used, he used the fundamental solution and some functional inequality, which is called the Nash inequality. And then in 1960, Moser, knowing both the results of De Giorgi and Nash, adopted a new approach where he, instead of also the isoperimetric argument, he used Poincaré inequality, and he used also an iterative argument on the logarithm of solutions. And this new approach also allowed him to get some Harnack inequality. So now in the kinetic context, why we are interested also in the rough coefficients. So if I just recall very shortly the Boltzmann equation, when we are considering long-range interaction, it means that the grazing collisions dominate. And then we have a singular Boltzmann collision operator. And here we are mainly focused on the Coulomb interaction. And in this case, it's ill-defined for the Boltzmann collision operator. So that's why Landau introduced another operator, which is kind of a limit of the Boltzmann one, which is well-defined and which looks like that. So you can see that it's not really a nice operator since you have a mix of V and V star on the derivative. Also, you have the projection along V minus V star orthogonal. And you take the divergence of everything at the end also. But the idea is to see this nonlinear equation still that that you can see that you can rewrite it in this way, where again it's a nonlinear equation, but the coefficient A of f and B of f, the idea is to see them as a general coefficient which are only measurable as the Giorgi-Nash-Moser methods. And so that you can see that if you get the results for the kinetic Fokker-Planck equation, then you deduce the results also for the Landau equation. So the main question we're interested in for the Landau-Coulomb equation is the Cauchy problem. Do we have existence, uniqueness, and regularity of the solution? So there are some existing results when we are near the equilibrium, but far from the equilibrium, it's a question which is quite open. And the best that we can do for now is to do some conditional regularity, in terms of regularity, I mean, it's to prove some conditional regularity results. So it means that we assume that we have some bounds on the hydrodynamic field. We assume that the mass, the energy, and the entropy are bounded. And the steps to be able to get the C-infinity regularity for the solution of the Landau-Coulomb equation are to first prove that the solutions are bounded, and then from the boundedness to go to the Hölder continuity, and then from the Hölder continuity to go to the C-infinity estimate. So for the L infinity, it's also quite open. We have some results for moderately soft potential, but for hard sphere and very soft potential, it's very open. To go from the Hölder continuity to the C-infinity, there is a work of Humbert and Mou, very recent work where they got some Schauder estimates in this case, which allow them to do this step. And for us, we are interested in getting the step to go from the L infinity bound to the C alpha Hölder continuity. So I'm going to give you some literature about this, how to get the Hölder continuity from bounded solution for the Landau equation. So we come back to the kinetic Fokker-Planck equation this time, assuming that the solution of the Landau equation are bounded and the hydrodynamic fields are bounded. We deduce that we can see the Landau equation in the good form so that we can see it as a kinetic Fokker-Planck equation. And so the existing literature about the kinetic Fokker-Planck equation is the following. So there are two methods which have been used, the Khrushchev-Moser method and the De Giorgi method. So first, the Khrushchev-Moser method has been used by Pascucci and Polidoro to prove the first results of boundedness of the solution. Then a bit later, Wang and Zhang managed to prove the Hölder continuity of the solution. But in the case where in the kinetic Fokker-Planck you don't have the drift term and the source term. So then the idea to be able to use it for the Landau equation, of course we need the drift term and the source term in this case. So the idea was to extend their proof. There is a first work of Golsenberg-Moe-Wasser where they extended it, but they used a different method. They used the De Giorgi method in 2017. And they used the De Giorgi methods, but the proof was non-quantitative because of one step of the method, which is the intermediate value lemma that I will describe just after, but which wasn't quantitative because it was using some compactness arguments. So then we wanted to get something which combined everything, both the quantitativeness and the fact that we have the drift term and the source terms. So we investigated two methods in parallel, one with Cyril Imbert, the Khrushchev-Moser method, and we got some results. So we investigate this method. We change a bit the point of view of Wang and Zhang, which were dealing with so the intermediate step in that proof were working for solution. We adapted them for sub and super solutions, so that we had to change the geometry of the cylinders to be able to do so. And the fact that we got results for sub and super solution, the intermediate step, it allowed us to get a new Guerand inequality, which works for super solution. And we deduce also then the quantitative Hölder continuity and Guerand inequality. And at the same time, we investigated the De Giorgi method with Clément Mouot, which is known to be quite robust and to apply to many equations and also classes of energy estimates. So to be able to do so, to get a quantitative De Giorgi method, so we knew that in the elliptic case, the method was quantitative, but in the parabolic case, we couldn't find any references. So it was one of my first work to get a quantitative version of the De Giorgi method in the parabolic case. So in particular, getting an intermediate value lemma, which is quantitative. And then with Clément, we managed to do a proof for the kinetic Fokker-Planck equation, which is different from the parabolic case. Also, that I will detail a bit here. So this is the main new results of our paper, and also in the paper we simplified a bit some existing proof, and the idea was to do a paper which is self-contained and which is short. It's about 15 pages. So I'm going to now to just explain a bit the steps of the methods, the two methods, and the differences between the two methods. So for both the De Giorgi method and Moser-Krushkov method, the idea is to get a main lemma, which is in red here, which is called the measure two-pointwise estimate, and which states that if you have a solution or a sub-solution which is smaller than 1 and with enough mass below 0, it means that it's below 0 in a non-zero measure set, then it will be not. It will be even more smaller. So it will be smaller than 1 minus mu in a smaller cylinder. And when you get this measure two-pointwise estimates, then it's almost finished, because from this measure two-pointwise estimates, it uses only scaling arguments and covering arguments to get order continuity, Guerand and Arnac. Also, you use an L2 and infinity estimates to get Arnac. But yeah, to get order continuity, you use the scaling argument combined with the the decreasing of the oscillation that you study. And so the main difference is of the two methods is in the way that you obtain this measure two-pointwise estimate. So for the De Giorgi methods, you have two tools which are called the first and the second lemma of De Giorgi. So the first lemma of De Giorgi is an L2 L infinity estimate. You can bounce the L infinity norm by its L2 norm. And the second lemma of De Giorgi is the intermediate value lemma, and it states that so if you take k smaller than r, so small value, big value, if you have some mass below a small value, it means it's the measure of the points where f is smaller than k. And if you have some mass above a big value, then necessarily you have some mass strictly in between the two values. And it's quantitative when you can have such an inequality which quantify these facts, that if those two quantities are non-zero, then you have this one. And in the kinetic case, I will explain, we have a slightly weaker version of this inequality, but which is still enough to get to do the De Giorgi method. In the Krushkov-Moser, so instead of having an intermediate value lemma, we have a Poincaré inequality. And the difference also is in the way in which we apply those lemmas. So in the De Giorgi method, we apply the lemmas to linear transformation of solution or subsolution. In the Krushkov-Moser, we apply it to the logarithm of solutions. So in some sense, for example, for the De Giorgi classes, the De Giorgi method is more stable in this sense. So now let me start with the talk. So I will first talk about recall some definition and give and explain the theorem that we are proving. And in the second step, I will talk about the intermediate value lemma and give some elements of the proof. And if I have some time, I will talk briefly about how to get the measure two-pointwise estimate, where we have the first and the second lemma of De Giorgi, and the main ideas of the Guerand inequality. So first, let me recall the kinetic Fokker-Planck equation. So in the next step, I will forget about the drift term and the source term, since it's written, but for the talk, it's not necessarily to deal with them, to make it simpler. So we have a solution of this equation in a bounded open set of R2D plus 1. So we have one dimension in time, D dimension in space, and D dimension in velocity. and consider A to be a measurable matrix of coefficients in all the variables, and we have the bounded condition and the ellipticity condition for this matrix. And we consider here solution in the following weak sense. So we assume that F is in the following functional space, which is relevant in terms of energy estimates. So we have the boundedness in time, L2 in space and velocity, and L2 in time and space, H1 and V. And to be solution, you just need to satisfy the equation in the distribution sense. To be sub-solution and super-solution, it's a bit more tricky. We also wanted some equivalence definition, but it seems to be not strong enough as a definition. So for example, for sub-solution, we consider test function, which are non-negative. And the idea is to multiply the equation by a test function, to integrate and to put one derivative in the test function. But then you got this inequality. But then the idea is to get this inequality not only for f, but also for any g of f, where g is a convex and non-decreasing function. And so we want to add this condition because we want, for example, if you have a sub-solution, if we remove a constant and we take the positive part, we want it to be still a sub-solution. And it's not clear that it will be enough to just consider a definition with f here. But this notion of solution in the weak sense for sub-solution seems to us that in the literature it was the weakest we can find. And it allows also to consider indicator function. As I will introduce later, I will introduce some example of sub-solution which are indicator functions. And we want them to be indeed sub-solution to have to be able to prove that the geometry that we use is optimal in the theorem. Let me introduce now the kinetic cylinder that we use and the scaling invariances of the equation. So we know that if we multiply the time variable by a coefficient R2 and the space variable by R3 and the velocity by R, the solution remains a solution. For the translation, it's a bit more tricky. So if we do translation in time and in space, then it's as usual, you just remove T0 and X0 and you still a solution. But if you also do translation in speed, then as you can see, so in the variable of velocity, you will have v minus v0. So somehow here you want also v minus v0 to appear. And so you need also to do a translation in space to compensate this v0 that you want it to appear here. And so that's why we consider the following kinetic cylinder. So we start with a unit kinetic cylinder, which is the following Q1, which is -1, 0 in time, and B1 in space, B1 in velocity. And when we use the scaling invariances, we deduce the general kinetic cylinder, which is obtained with a Galilean transformation. And where you can see that it's not a straight cylinder, it's slanted. And you can see that the center in X also moves with time. So you start, for example, at time t0 from x0, but it will just move with time. and it will be slanted. So now, yeah, you have also the same definition with the drift term and the source term. So I won't spend much time on it. And then, so let me introduce the main theorem. So it's about always about interior results. Won't mention it again, but every time we'll have an estimate. The cylinder in the left-hand side will be smaller than the cylinder in the left-hand side. So for example, for the Hölder regularity, we consider a solution in a big cylinder Q2, which is represented here. And if we move away from the boundary and from the initial data, we have the Hölder continuity. And we have this inequality, this estimates, and the constants in this estimate. So both the here it means that it's up to a multiplicative constant depending only on the dimensions and the bounds of the Hessian matrix, and it's said to be universal. So when we write an inequality, it will be always universal multiplicative constants. Also, the alpha will be universal, and moreover, all the constants will be computable. It will be a quantitative. We also have the Harnack inequalities. So here we are dealing with time-dependent equations. So we need to consider cylinder of the future and cylinder of the past. So we have a cylinder here, Q minus R0. I will say after why we need to introduce cylinder of radius R0 here. We need cylinder of the future, of the past and of the future. And the difference with the parabolic case is that the cylinder needs also to have a gap in between, which will be big enough, and that I will explain also just a bit later why we need this gap. And so we have the usual Harnack inequality here, which says that if you take F a solution, you can bounce the supremum in the cylinder of the past by its infimum in the cylinder of the future, up to a multiplicative constant, which is universal. And you have also, we prove also a weak Harnack inequality, which is true also for super solution. And instead of having the supremum, in the left-hand side, you have somehow a quasi-LQ norm, where Q is not necessarily bigger than 1, but it can be very small, close to 0. And usually it's very close to 0 also. So we have this theorem, and they all comes from the measure 2-pointwise lemma that I introduced, and I will explain the intermediate value lemma, which is one of the steps which allows to get this measure 2-pointwise lemma. So let me first introduce some tools that we use in the proof, some functional inequalities that we need. So we have, if we consider a subsolution which is non-negative, we have both estimates. So we first have an energy estimate, which gives us some an infinity control of in time of the L2 norm in X and V, and we can control also the H1 norm, so of in velocity of F. But as we can see, we don't have any information in the variable X. So this is missing in the energy estimates. And this information is useful for both the first and the second lemma of De Giorgi, actually, getting some information in the X variable. So in the literature, you could find some information in the X variable, some gain of regularity in the X variable using either the averaging lemma or the fundamental solution. So here we use the fundamental solution to be able to get first an LP estimate. So we know that the solution is in L2. We want a bit more. We want LP strictly bigger than 2. And to get this, we use the fundamental solution, some estimates on the fundamental solution. So we revisited some existing proofs of Pascucci Polidoro and Humbert Silvestre, for example. And we got also a new estimate for the, so yeah, I forgot to mention, this LP estimate is useful to get the first lemma of De Giorgi. So when you have a bit more than L2, you can iterate with either the De Giorgi iteration or the Moser iteration and get the L infinity bound. For the intermediate value lemma, we needed also some gain of regularity in X. And we managed to do so again using the fundamental solution. So we got some W sigma 1 estimates, where sigma is between 0 and 1/3. Okay, so let me explain now with those tools how we deal with the intermediate value lemma. So first, we'll recall the results in the parabolic case, and we'll see a bit how to introduce the kinetic, how to understand and introduce the kinetic case. So in the parabolic case, we consider a subsolution and prove actually an intermediate value lemma which works for subsolutions. As I said before, it's useful to get the weak Guerand inequality which works for supersolution. So we need to cut the symmetry in sub and supersolution to get an weak Guerand inequality. So in the parabolic case, we know that we need to introduce a cylinder of the past and a cylinder of the future, Q1 minus and Q1 plus, which are disjoints, but we can touch each other like that. And then, so the intermediate value lemma is the following. If you have some mass in the small values, so with A strictly smaller than B, if you have some mass below A and some mass above B in the cylinder of the future, then you necessarily have some mass in between in the cylinder Q2. And we can't do better than having this separation between Q1 minus and Q1 plus, because we have some existing subsolution which admits a jump in time. So for example, we have this one which is equal to the B, the big value first, and then A, the small value. And we want it to not be a counterexample, of course, of the intermediate value lemma. So it also proves that we can't do better than that, and we really need those cylinders to be disjoint like that, and to have the small values in Q minus and the big values in Q plus. So in the kinetic Fokker-Planck case, we have some similarities. So we still have subsolution which can do a jump along an hyperplane in both time and space. So for example, here in orange, there is an hyperplane discontinuity where you have the value B below the hyperplane and the value A above the hyperplane. And again, then you see that you don't want the two cylinders to cross both the hyperplane, because it will mean that you will have some mass below A and above B in both the cylinders, and then you can have something which is non-zero in the left-hand side and something which is zero in the right-hand side. So we really need cylinders which are separated enough with a big gap, big enough, so that an hyperplane of discontinuity can't cross both of them at the same time. We know also that the hyperplane, in any case, have a slope which is bounded, so we just need to separate them with thanks to these bounds. So it's bounded by the maximal velocity, the slope of this hyperplane, which is useful here. In the kinetic case, so we get some kind of similar intermediate value lemma with Clément, which is a slightly weaker version of it. So instead of having an inequality that you can write in this way, you assume that the two quantities being below a small value and above a big value satisfy some proportion delta 1 and delta 2 of the cylinder. So we fix first the two proportion delta 1 and delta 2. And then we have the existence of some constants. So the existence first of the new constant, which is the one that we need. We need this one to be strictly positive. Those two are strictly positive. And it satisfies also some condition which depends on delta 1 and delta 2. We have a quantitative estimate for that. Another difference, which is that in the parabolic case, we could allow any jumps, we could allow any A and B. Here, if we fix, for example, A equals to 0, the B will be determined by delta 1 and delta 2. It will depend on those two parameters. But so we can't do a jump which is fixed already delta 2. And we also fix the size of the cylinder, which comes from the proof. We need to take a cylinder small enough in the proof to get this lemma, but it's not a problem since after that we use the scaling arguments, so we can still we recover the lemma, the Hölder continuity still in the end. And so, yeah, in the picture you can see that if you have some mass below 0 in the cylinder of the past and some mass above 1 minus theta in the cylinder of the future, then you necessarily have some mass in between in the big cylinder Q2. Let me now give some elements of the proof. So the main idea is to first prove a weak Poincaré inequality, which worked for the kinetic Fokker-Planck equation. So we consider a non-negative subsolution F, and we want to prove this Poincaré inequality where it's weaker in some sense, because so we have some differences with the usual Poincaré inequality. First, instead, so here it's supposed to be the average, there is a bar missing, but instead of taking the average in the same cylinder, we need to take the average in a cylinder that I introduced before, which is disjoint. So here we have Q1 plus, but here we have Q1 minus. And instead of taking the absolute value, we take only the positive parts. So we need to do that because otherwise we have counterexamples which are exactly this kind of function. It shows that it can't be the usual Poincaré inequality anyway. And so in the right-hand side, we want to bound it with the L1 norm of the gradients in velocity. So we would expect to have also some derivative in time and x, but it's not enough then to get the intermediate value lemma. We really want only derivatives in velocities. So I'll explain how we can just deal with this. And also we need to add some error term So some epsilon of the L2 norm of F that we will see also in one step of the proof why we need to introduce this. So the idea of the proof is to consider what we have inside the positive parts. We can put this integral in factor somehow just before this F and deal with the difference of the two F. So we have one F integrated in the Q1 plus, which will have the variables T, X, V, and the other F, which is integrated in Q1 minus, which is a variable S, Y, and W. So we consider this difference and we estimated it. To do so, we construct a trajectory to go from this point to this other point. So we know that if we move along velocity, then using a Taylor formula, we'll be able to recover what we want. So exactly an L1 norm of the gradient of F. You can see here, for example, we just changed the velocity with using a Taylor formula. We have what we want, but we want also to move in time and space. This one is a bit more tricky. If we just move first in time and then in space, we will have some terms that we don't want. So the idea here will be to move directly along the transport term. So why the transport term? It's because if we manage to get the transport term here, then we'll be able to estimate it with the diffusion term, and the diffusion term contains derivative in velocity, what we want. So we will just need some more computation to deal with this term afterwards, but at least we get rid of the derivative in time and in X. And so to find this good trajectory, we need to introduce an intermediate velocity, capital V, which is X minus Y over T minus S, which is exactly the good velocity to be able to consider the transport term here when you compute a Taylor formula, so that you will have the good velocity in V here and in the third variable when you compute this. So you introduce this intermediate velocity, and then so you move first in velocity, then along the transport term, and then again along the velocity to recover the last point. And so the idea behind this of using both the vector fields of the gradient in speed and the transport term is that we know that with our Mander commutator, those two vector fields span all the directions. So somehow this idea is hidden in the proof. And also it gives us hope to deal with other equations. So we are already dealing with, for example, we are working on an extension to the ultra-parabolic case with Clément, Francesca, and Anna Laura. And also, as you can see in this intermediate velocity, so we have the T minus S in the denominator, and we want this velocity to remain bounded. So you can already see in the proof that so T is in the cylinder of the future and S in the cylinder of the past. For this to remain bounded, we really want a gap between the two cylinders. Let me do just a focus on this term to explain how we can deal in the end with this term. So if we zoom in this Taylor formula here, so we managed to control the term in the middle thanks to the Taylor formula that I wrote here. Here we have the intermediate velocity, which is both in this place and in this place, so that we can apply the equation and bound it with the diffusion term. Now in the diffusion term, what we want to do, so I also put some test function, which is here for to do the computation anyways. To go further, so what we want to do is to perform an integration by parts. So we want to put this derivative on the test function file. But to do so, we need the variable along which we will do the integration by parts. So which one can we use? X, Y. The problem is X and Y are in both in second and first position, so we can't do the integration by part like that. So the idea is first to do a change of variable. It would be good if we could do directly a change of variable with X and Y, but it's also not really possible because we can't use the integral in X at this stage. So why? Because the integral in the cylinder of the future is outside of the positive parts. We can't put it inside because we will lose many information. So we can't use the X variable actually to perform a change of variable. We can only use the variables which are in Q-1, so S, Y, and W. And so then we only have Y here. We don't have enough variables to do this integration by parts. So that's why we need a bit more, that's why we needed this estimate in X. We will artificially use move in a small move of side epsilon in W, so in space. So we will move from X to X plus epsilon W first to be able to introduce the variable W here and to do the computation that we wanted. And now we are able to do the change of variable and the integration by parts without any problem. And that's why we needed the W sigma 1 estimates in X. And this term makes it appear here, the small error term. And also we have a factor 1 over some epsilon to the power of something in front of, to compensate in front of the gradients in velocity. Okay, I will just explain briefly how from the Poincaré inequality we can deduce the intermediate value lemma, and then I think I will stop here. So we recall that for the intermediate value lemma, we fix first delta 1, delta 2, and we have those two assumptions. We consider a subsolution which is smaller than 1 also in the theorem. And we apply the Poincaré inequality, which works only for non-negative functions. So we apply it to F plus. And the idea here in the Poincaré inequality is to estimate the left-hand side from below, and to be able to estimate it from below with some constant depending on delta 1 and delta 2, and to estimate the right-hand side and where the measure of the intermediate value will appear. So we'll see how. So by doing some few estimates, we are able to bound the left-hand side from below by some term which depends on delta 1 and delta 2. I will just explain the second step where we want to bound the right-hand side. So for the right-hand side, the idea is to divide the integral in 3 pieces. So one piece where f is equal to the set where f is equal to 0, where f is strictly between 0 and 1 minus theta, and one piece where f is bigger than minus theta. So the first integral where f is equal to 0, the gradient of f plus is equal to 0. So the first one is equal to 0. The second one is the one which will help us to make it appear the measure of the intermediate volumeter. Because first, so we can use the Cauchy-Schwarz inequality, seeing this as an indicator function. We use Cauchy-Schwarz, and then we have the square root of the L2 norm. We have the L2 norm of the gradients. We have the square root of this measure, and then, so to get rid of this L2 norm, we use an energy estimate. The energy estimate, we can bound the H1 norm of F by the L2 norm. And we know that F is smaller than 1, so this is bounded by a universal constant. We have what we want. And for the third term, so we show that it's something which will be an error when we will choose theta. That's why we need to fix theta. So here, the idea is first to see that this integral is equal to this one. Because if you are smaller than 1 minus theta, anyway, it's like having a function which is 0. And so which is 0 here. And if you have f bigger than 1 minus theta, then you just, this will be exactly the gradient of f plus anyway, because the constant will disappear with the gradients. Then we perform a Cauchy-Schwarz inequality, and we use to get the L2 norm, doing the same step as before, combining both the Cauchy-Schwarz and the energy estimates. We are left with this, and the f, we know that it's smaller than 1, so we are left with something smaller than constant times theta. Then if we combine both inequalities, the bound from below and the bound from above, combining both, so we have some delta 2, delta 1 in the left-hand side. Here, this is the term that we want. And now we want to make this one small and this one small, that they will compensate with this one. So we first take, we put the condition on epsilon such that this will be smaller than delta 1, delta 2 over 4 to be compensated with this. And this one also to be compensated in the same way. And then we are able to get so an estimate for the measure of the values where f is between 0 and 1 minus theta. So we find our new here. So, okay, I think I will stop here. Yes, as I said, there are still many open questions, like the non-divergence case, for example, and yeah, the ultra-parabolic case is a work in progress. And yeah, I will stop here. Thank you.
Thank you very much for this very nice talk. So does anyone have a question or a remark? If this is the case, please turn on your camera and unmute. So. Okay, maybe I go ahead, because I mean, I have to say I'm not an expert, so my question might be quite naive.
That's not
Looking at the intermediate value lemma that you derived, you said in the parabolic case you could allow for any jump from A to B, while for the kinetic equation you can only allow for certain jumps from 0 to 1 minus theta. I was just wondering, does this make sense in this from a physical interpretation, that actually not all jumps that is not not happen in terms from the just by the modeling of the equation? I know this might be very naive, but I was just
exactly.
This is also something that you actually don't want anyway. So yeah.
Yeah, exactly. You would expect to also allow any jumps, to not allow any jumps also in the kinetic case. So here it's really linked to the fact that we got this weak Poincaré inequality in the kinetic case, and the fact also that anyway it's enough to have one fixed jump to get the Hölder continuity, And it's easier to prove this lemma, and it's enough to get the results. So we focus on that. But yeah, if one day we manage also to prove it for any jumps, it could be a good, a good result.
Thank you. Any other questions? Okay. So if there are no questions, I would like to thank you very much for your talk.
Thanks to you.
We will reconvene. So we have a 20-minute break. So we will reconvene.